All right, so properties of compounds here, guys. Okay, first off, we're going to go over the properties of compounds, hence the name of the lesson. Okay, acids, bases, ionic compounds, molecular compounds. What are some things they have in common? What are some things they have that are different? But most importantly, how can we use those properties to identify a bunch of unknowns? Which is what you're going to be doing in your lab on Wednesday. Okay, so on Wednesday you're going to have a lab where I will have a whole bunch of beakers along the desk. Okay, they'll be labeled A through like J or K, something like that. Okay, they'll be labeled just with a letter, and you're going to run a series of tests on them, and from those results, you're going to have to tell me from a list of identities, okay, compound A was sodium chloride, compound B was copper sulfate, compound C was hydrochloric acid, okay, things like that. You'll have to identify them just from their properties, their physical properties. So that's why we need to go over what some of the physical properties are today. So if you see anything that you think, while we're going over these notes, would be really useful in identifying a compound, okay, make sure you highlight it, okay, or write it down or whatever it is you do for your note taking, okay, so that when it comes to doing this lab report, you can refer back to these notes and go, oh yeah, I remember Mr. Quader said all compounds that contain nickel are green. Okay, and so that there was a green one. It must be nickel then. Okay, something like that. So everyone kind of follow me on that one? Okay, so that's kind of what you're going to be watching for a bit today. All right, questions on that? Okay. All right, so first off, all matter has certain properties. There's chemical properties, and chemical properties are not evident just from looking at something. A chemical property only becomes evident in a reaction. So when something reacts with something else, that's a chemical property. For example, okay, sodium metal is highly reactive with water. Right? You wouldn't know that just by looking at it, okay, but it is. Okay? In fact, if you take it out of its container, it will react with water vapor in the air, somewhat violently. Right? So yeah, it's kind of a dangerous thing to have around. Right? We're not even allowed to have it in the lab anymore. Okay? We used to have it, and it would come in a glass jar filled with kerosene. Right? And the metal would be sitting in the kerosene, so it couldn't come into contact with water vapor in the air. It's that reactive. Okay? But again, you don't really know that just by looking at it. Like, oh, there's a chunk of metal sitting in that stuff. Okay? It doesn't really look like it would blow up in your face. Okay? But it would. Right? So it's not chemical properties are not necessarily evident, okay, until the reaction occurs. Physical properties, however, are. They're easily and readily observable, okay, just by having a piece of that stuff in your hands, looking at it, okay, or running very simple tests, okay, like for example taking its mass, right, and figuring out what its density is, heating it up and seeing at what temperature it melts at. Things like that are physical properties. So melting point, boiling point, color, okay. Other things could be the ability to conduct electricity, whether it's attracted to magnets or not, whether it dissolves in water easily or not. If it's ductile, okay, or is it malleable? Okay, ductility means that it's somewhat flexible. You could draw it into a wire easily. Okay, malleable means that if you pound it with a hammer, you can change its shape without it breaking. Right, so like metals are typically quite malleable. If you hammer on them, you can change their shape. Okay, whereas minerals and stuff like that, if you hammer them, they just break. All right, everyone follow there? So those are all kinds of physical properties. Okay. That we could use, okay, in order to identify something. So that's what the kind of stuff that we're going to be going over today. All right, for ionic compounds. Okay, now an ionic compound has what two things in it? A metal and a non-metal. Okay, so it's important for us to remember that. Anything that has a metal and a non-metal in it is going to show certain properties. Okay, and molecular and ionic compounds generally differ on several fronts. Okay, there are a few that are 100% of the time right, and a few that are like 80% of the time right. They're still useful, okay, in terms of identifying or separating something as ionic or molecular. All right. First off, ionic compounds typically exist as crystalline solids, which we call salts, okay, at room temperature, and they have very high melting points. Okay. Are there some molecular compounds that could be crystalline solids? Okay? Molecular compounds are made up of just what? Nonmetals, right? Just nonmetals. So sugar is made of carbon, hydrogen, and oxygen. So is it molecular? Yes, it is. Okay. Is it a crystalline solid? Yeah, sugar's a crystalline solid at room temperature. Okay. So like we said, all ionic compounds are, but that doesn't mean there aren't some molecular compounds that aren't also. Okay. So yes, if something is a crystalline solid at room temperature, it's likely that it is a ionic compound. Okay, but we maybe have to perform other tests just to be sure. Okay, ionic compounds will conduct electricity when they are in solution. That is true 100% of the time. Okay, so if you ever have a crystalline solid and it's unknown, if you dissolve it in water and it conducts electricity, you are 100% sure now that that compound is an ionic compound. Because if you do that with sugar, it won't conduct electricity. Okay, so you'll know, okay, that was a crystalline solid, but it's molecular. It's not an ionic compound. And that would help you in terms of being able to identify it. Okay, if you had three unknowns, let's say you had sugar, salt, and let's say calcium fluoride. Okay, well, you got two ionic compounds there, one molecular, but all three are crystalline solids that are clear. Okay, well, you'd be sure to identify sugar from just doing a conductivity test. All right, and that's because of what we talked about the other day, where when ionic compounds are made, they get this this charge, right? The metals give their electrons to the nonmetals, so the metals become positively charged, and the nonmetals become negatively charged. Okay, when they go into solution, and then as a result, they conduct electricity. For sugar, you put it in water, it dissolves, but it doesn't dissociate like that. It stays as a full molecule of sugar. It's just dissolved in water. All right, so those solutions do not conduct electricity. Everybody clear on that? All right. Now, another thing that ionic compounds typically do is that they are quite soluble in water. Okay? They're usually highly soluble in water. Are there molecular compounds that are soluble in water? Is sugar soluble in water? Yeah, I mean, you wouldn't be able to make soda pop, Gatorade, or any of those kind of stuff, or sweeten your coffee for that example, for that matter, without sugar being soluble in water. Right? But again, we'd know sugar was a molecular compound after we did the conductivity test. Right? But generally, okay, your ionic compounds are soluble in water, and generally, your molecular compounds are not. Right? For example, butter is a molecular compound. Does it dissolve in water? Oil, same thing. Okay, candle wax, it's a molecular compound, doesn't dissolve in water. Okay, stuff like that. All right. So if you look at a single grain kind of an ionic compound, you're going to see a crystalline shape. All of them are different, just like snowflakes. Okay, every compound's crystalline structure is slightly different. Now, unless you can, look at them under a microscope, you're never really going to know that, right? But obviously, you've seen sugar and salt side by side, and while from far away they look kind of the same, closer up they're very, very clearly different. Okay, the crystals have different shapes. All right. Showing you here, okay, I mentioned just a few minutes ago that nickel-containing compounds are always green. Okay, that's also in your notes package. Okay, but if you had a crystalline solid and it was green, it probably contains nickel. So if one of your unknowns was, let's say, this, and you had a green crystalline solid, that's probably it. Okay? Everyone all right with that? Okay, many ionic compounds produce solutions that are brightly colored. Okay, so we just talked about how nickel compounds are green. Okay, cobalt-containing compounds are pink to red. Okay, pink to red. Usually by the time you get them dissolved, they're kind of a pinkish color, but the solids themselves can actually be kind of red, almost like blood red. Right? And copper-containing compounds are always blue. Right? So I would say those three are pretty important because I never do this lab without a cobalt compound, a copper compound, and a nickel compound. All right? So there's going to be one of each. I guarantee it in this lab. All right? So you got to be looking for something that's blue, something that's green, and something that's reddish pink. All right? Okay? And again, we're talking here about ionic compounds producing solutions. Again, they're going to be soluble in water. They're going to dissolve fairly easily. Right? When we do this lab, we're going to have what's called a depression plate, which is a little ceramic rectangle that's got little pits in it. Okay, if you wear contact lenses, they're about the size of the little dip that you put your contacts in to clean them. Okay, they're about that size. And we're going to do all the tests in there. You can't put very much water in there, but you'll find that most of the ionic compounds will dissolve even in that small amount of water. Okay, they're going to be very, very soluble in water. Questions so far? All right, molecular compounds tend to be solids, liquids, or gases. So they can be any state at room temperature. All right, so if in the lab on Wednesday, one of your compounds is a liquid to start with, is it ionic or molecular? It's molecular, right? Because we already said all ionic compounds are crystalline solids at room temperature. So if you get a liquid, you know right away that's a molecular compound, and you've eliminated half of the identities from the list. Right? You've eliminated all the ionic compounds already. Okay, so it's going to be kind of a process of elimination type of thing that's going to go on there. Okay, we're not going to have any gases. It's really hard to keep them in a beaker for you to test, right? Okay, so we won't have any gases. And they have very low melting and boiling points. Now, we're not going to be testing and measuring boiling points and melting points in this lab just because we don't have the equipment for it. Okay, but that's why they can be solid or sorry, they can be liquid or gas at room temperature. All right, molecular compounds are not usually as soluble as ionic compounds, so that's something that's going to be useful to know. Okay, molecular compounds are generally not as soluble as ionic ones, and they do not conduct electricity. Sorry, their solutions do not conduct electricity. Okay, so in an ionic compound, you've got your positive and you've got your negative ion. Okay, whereas in a molecular compound, you just have these molecules that have no charge. Okay, no parts of them come off. Right, they stay neutral. Okay, and molecular compounds that do dissolve in water don't have any colors. Right? They always produce clear, possibly cloudy, okay, but still clear solutions. No bright colors like blue or pink or green. Right? So they're always going to be that way. Another example, okay, what's going on here is a process of distillation, okay, where they remove alcohol from water. Okay, alcohol is a molecular compound. It's made of carbon, hydrogen, and oxygen. Okay, and so it is obviously clear. Does it dissolve in water? Good, no one answered. See, that's good because you shouldn't know that. You're not old enough yet. Okay, alcohol does dissolve in water. Okay, you can put it in water and stir it, and they don't separate. Okay, it's not like oil and water, where if you put oil in water and stir it, it'll eventually sit back on top. Okay, alcohol dissolves completely in water, and it's clear. Okay, so it makes a clear solution. Everyone with me there? Yeah. Okay. Okay, acids. Are acids dangerous? Some of them are, yes. Strong acids are dangerous, okay? Weak acids are not. Okay? When you drink orange juice, I don't think you consider that to be dangerous. However, it is acidic. Okay? Lemon juice, same thing. May not be all that pleasant to drink, but it is acidic. We have lots of acidic things in our diet. Okay? Vinegar is also an acid, right? But okay, it's not harmful as long as you don't have it in the concentrations we have it in the lab. Okay? We have what's called glacial acetic acid, which is vinegar that is hundreds of times more powerful than the stuff you buy at the grocery store. Okay, you spill it on the tabletop and it'll eat a hole in it. Okay, yeah, so pretty dangerous stuff. Yeah. Okay, come on, you're gonna have toys. You gotta have toys that are fun. Okay, that's the way we look at it in chem. All right, so acids have H+ ions in them. So if they have ions in them, they must be what kind of compounds? Ionic, okay? So if you have a strong acid, it's going to be an ionic compound. Weak acids, okay, tend to be molecular usually, all right? Citric acid, the stuff that's in orange juice and lemon juice, is a molecular compound, okay? It's a weak acid, all right? Anything that has a pH of less than 7 is considered acidic. Now, consider this. Acid rain, okay, would have a pH of around 3. Normal rain has a pH of around 5. So it's actually a bit acidic. But do you consider rain to be an acid? Generally not. Okay? I mean, if it was, thunderstorms would probably be a lot more concerning. Okay? But rain, even good rain, is naturally slightly acidic. Okay? Now, the acids that we're going to have in this lab, there's going to be no questioning it. It will be very obviously acidic. I'm going to make them concentrated enough that when you put the pH paper in them to test, it's going to turn very bright red and say it has a pH of 1. All right, that's about as acidic as you can possibly get. Okay, so if something is an acid, it's going to have H plus in it. Now, remember that H, hydrogen, can be a metal or a non-metal. How do we know if it's behaving as a metal? It's positive, and in the compound, will it be first or second? It'll be first. Okay? So, for example, hydrochloric acid or hydrogen chloride. Okay? H is listed first, so it's behaving as a metal. That means that when I put this in water, it will split into that, H plus and HCl. All right? If I had this stuff, same thing. This is hydrogen fluoride, okay, or hydrofluoric acid. So this would be H plus and F minus when I put it in water. Anything that when I put it in water will release a positively charged hydrogen ion is behaving as an acid. Okay, the presence of positively charged hydrogen ions floating around is what makes something acidic. Right? Now, these two things, they can be quite acidic. This is the stuff that's in stomach acid. Right? Your stomach has around a pH of 2 in order to properly digest food. Okay? Now, other acids, possibly stuff like this. Okay? Which do you think is going to be more acidic, this or these? If the ability to give off positively charged hydrogen ions makes you acidic, would the ability to give off more of them make you more acidic? Yes. So the more hydrogen ions a compound can give off, the more acidic it's going to be. Right? So for example, with this could give off 2 hydrogen ions. This is sulfuric acid. It's very, very harmful stuff. Right? This stuff's even worse. Nitric acid. Okay? In fact, all acids, but this one in particular, can become a vapor. Okay, and the vapor can do a lot of damage. Right? We were doing something in high school. I don't remember what now, but we were using that. And one of my lab partners was the setter on the volleyball team, and he left the cap off of this stuff, and he was working around it, and he had his hands kind of over it. And within a few hours, he had chemical burns all over his hands. Okay, because the vapor had actually gotten onto his skin and then chemically burned his skin. Okay, couldn't play for like 2 weeks. Because he had chemical burns on his hands. So they can be very, very dangerous, even in a vaporous form. Okay, I've had this stuff knock me flat on my back when preparing a lab before, because again, I left the lid off. Okay, and I just went over and I reached for something that was over on the other side of it, and I sneezed. Okay, and when I sneezed, then I inhaled and I sucked in a whole bunch of the vapor. Okay, flat on my back. Okay, one of my colleagues came in, I don't know how much later because I was unconscious. Okay, and they woke me up and I had blood all down my face and neck because it just goes into your sinuses and eats away, causes a big nosebleed. It's nasty. Okay, so all of these things can be very harmful in very concentrated forms. So we should not be doing any taste tests with any of the unknown compounds on Wednesday. Agreed? Yeah. It'll taste very, very sour, and it'll be the last thing you ever taste. Okay? So yeah, don't taste anything. All right? Everyone's clear on that one? Okay. Now, they also, acids also tend to have a vinegar-like smell. Okay, obviously acetic acid smells very much like vinegar because that's what it is. Okay, but all acids tend to have that sharp smell to them, that vinegar has. So, how do I smell one of these without getting knocked flat on my back like I did? What's the proper technique for smelling an right? I see Mike back there doing this. Okay, you waft it. Okay, you guys have been taught that before. So you hold the beaker, okay, a little ways away from you, and you waft, okay, the fumes towards you, and you inhale the fumes just a little bit. Okay, you don't put it over underneath your nose and go. Okay, if you snort that stuff, you will regret it. Okay, it'll be very, very bad. All right, so you don't want to do that. Okay, so we just waft things if we want to smell them. In our lab, there's only going to be two things that have any kind of odor anyway. All right, and they will be very, very obvious. Okay, the strong acid will have the sharp vinegar-like smell. Okay, and alcohol is also going to be one of your unknowns. Does alcohol have a distinctive smell? Again, you're not supposed to know the answer to that, but it does. Okay, it does have a very distinctive smell. Okay, rubbing alcohol you've probably smelled before. It's the stuff you use to sterilize cuts and stuff. Okay. All right, so big thing to remember here, acidic solutions have a pH less than 7. So one of our tests in this lab is going to be a pH test. You'll get some pH paper, little litmus strips, okay, that you can dip in the compounds and check them, okay, for their pH, and then get that off of the little color chart that comes along with them. Okay, so acidic ions, or acidic ionic compounds, okay, are crystalline solids at room temperature. Okay. We can't even get them shipped to us that way. Okay? They will not ship acidic ions to us in solid form. They always come in solution. All right? Simply because if there's ever any spill, okay, it's way easier to dilute something that's already dissolved and diluted than it is to try and get rid of a solid and find all of it. So, okay, there will be one unknown, okay, that'll be dissolved in water for you already, and I'll tell you which one that is so you don't mistake it for a liquid. All right, everyone follow me on that? Okay, there'll be one like that. All right. Questions there? Okay, bases. There's strong bases and weak bases, just like there are strong acids and weak acids. And a strong base can give you just as bad of a chemical burn and have just as bad a chemical side effects as a strong acid. All right. For example, how many people have ever cleaned out their oven with oven cleaner, not by using the self-cleaning setting? Anyone ever sprayed that white foamy stuff inside? Okay, if you have, you know it has a very distinctive smell. It is incredibly basic. Contains something called sodium hydroxide. Okay, all bases contain this ion. They all contain hydroxide. Right? The more hydroxide they can give off, the more basic they are. Okay, everyone with me so far? Okay, so is this stuff an acid or a base? People aren't sure. What if I wrote it this way? Acid, base, or here's the third option, neutral. Neutral. It's water. That's why water's neutral. It has both in it. Okay? Normally it doesn't behave like an ionic compound, okay, but it can on occasion. Okay? And as a result it's neutral. Because it has both the the acidic ion and the basic ion in equal numbers. All right? For something like this, it doesn't. Okay? It only has the basic ion. So, when it dissolves in water, it's going to create a highly basic solution with a pH of like 14. Okay? All right, so they're typically ionic compounds unless they're a weak base. A weak base would be something like baking soda. Okay, baking soda is a weak base, right? So it'll have a pH of like, let's say 9 or 10. Right? Again, you use it in cooking. It's not harmful to you at all. Okay, in fact, it's usually what's in antacids and stuff like that. All right, bases typically taste bitter. Again, you're not going to be doing any taste tests in the lab. Okay, but generally they are bitter. All right. Baking soda tastes bitter. Okay, soap tastes bitter, right? Because it contains lye. Lye is highly basic, right? Stuff like that. Okay, and like we said, bases have OH ions in them. So if sodium hydroxide ends up being one of the unknowns, spoiler alert, it is, okay, one of the unknowns, and you get something that's highly basic, well, you need to look for anything that contains an OH ion. Okay, if it does, it's most likely, okay, this stuff here. All right, and like we said, basic solutions have a pH that is higher than 7. Alright, so questions on any of that stuff there? Okay, basically we just need to be able to refer back to this stuff when we're trying to find out the unknown, the identity, sorry, of our unknown compounds, right, on Thursday, right, when we're done the lab. Alright, now, I'm going to talk to you here in just a minute here about how we're going to set up our lab reports, okay, those kind of things, and then we might even have a chance to get started on it here.